So in this, so let me just remind you a little bit where we are. So we have this well-possessed result for rough data for the Einstein equation at the level of curvature in L2. And we have seen that one very important, crucial ingredient, I should say, to prove this result is to do bilinear estimates. There were also a set of Strickhardt estimates, but maybe more importantly, bilinear estimates. And we've seen also that to prove these bilinear estimates, you have to rely on the representation formula for the wave equation. Okay, so here let me remind you that the representation formula we have for the wave equation is the one that's written here. And furthermore, what is important in this representation formula is that it has a phase, it's a Fourier integral operator with a phase which satisfies the econal equation and which depends on an additional parameter omega, which creates difficulties of its own, as we saw this morning. And then this morning we have studied in detail the regularity of this equation, of the econal equation. And in particular, we have extracted as much regularity as we could, both with respect to space-time variables and with respect to this omega parameter. And now, whatever regularity we have obtained, we have to pray that it's going to be enough to do whatever we have to do for this parametrics, which means constructing it and controlling it. Okay, so let me maybe refresh the memory a little bit on these steps, because that's what I want to focus on in this lecture. I want to focus, well, actually, I'll do it reverse. I'll first focus on the control of the parametrics, and then I'll talk a little bit about the construction part of the parametrics. Okay? So remember that your parametrics is a Fourier integral operator. It's a sum of two half waves. So at first, I will forget about this sum and just focus on one half wave for the control, because that's enough. The two half waves is only important for the construction step. They are there to ensure that you can generate all the initial data of the wave equation. But in terms of estimates, whenever you estimate things, you just need one half wave. You estimate half wave per half wave, and it's just when you're trying to generate all the initial data that you need the two half waves. Okay, so for most of the lecture of this afternoon, I'll forget about these two half waves. And remember that you have a particular phase, which is EI, oscillatory phase, which is EI lambda u plus minus tx omega. F plus minus is here to generate any initial data, as we'll see later on. And so you have two things you want to achieve. The construction step is the fact that, again, remember, you're trying to approximate the wave equation. D'Alembert G of phi is 0, and phi on your initial slice sigma naught is phi naught, sorry. And T phi on the initial slice sigma naught is phi 1, where phi 0 and phi 1 are given functions. Okay, and sigma naught, again, as your initial slice. So you have your initial slice sigma naught, and T is the unit future directly normal. You're trying to approximate this equation, and in particular, you need to generate the initial data. So you need to make sure that your parametrics at initial time, in other words, satisfies the following problem. So you cannot have D'Alembert G of S is 0, as we saw, but it's just equal to this error term E that I'm going to talk in a moment. And then still you want to satisfy the same initial condition as the wave equation you're trying to approximate or to represent. So S on sigma naught is phi naught, and TS on sigma naught is phi 1. Okay, and so you have to generate all initial data, and not only that, so you have to prove, in other words, you have to prove that because of your particular choice of initial phase, and in particular because of this asymptotic behavior here, which relates it to the phase of the inverse Fourier transform, you have to prove that you can always find a linear combination of your plane waves. In other words, you can always find this F plus minus of lambda omega such that you can generate phi naught, S on sigma naught is phi naught, TS on sigma naught is phi 1. And furthermore, more importantly, you need this estimate to be to hold. And remember, this is the sharp estimate. This is sharp because it's the estimate you get in the flat case, just from Plancherel. Okay, so lambda F plus minus in L2 is controlled by nabla phi naught in L2 and phi 1 in L2. Okay, and then because it's not an exact solution, it's just an approximate solution, remember you have the error term, which is just D'Alembert G of S is equal to the error term. And the error term, as we have seen, so it's a Fourier integral operator with a phase which is D'Alembert G of U plus minus. But as we saw this morning, you can reinterpret it as the mean curvature of the level surfaces of the U plus minus Okay. We have seen that there is an explicit computation that actually gives you Dalmatian G of u plus minus is the mean curvature, is trace chi plus minus. Okay, now you have this Fourier integral operator with phase u and symbol mean curvature of the u foliation, and you want to prove the following control for the error term, which is you want to control in L2 the error term by lambda f plus in L2 plus lambda f minus in L2. And again, let me remind you that this is also sharp in the sense that if I take u plus minus is t plus x dot omega, and if I replace this by a smooth symbol, this is the estimate you would get. So this is the sharp estimate in the sense that even if you didn't have any regularity constraint, that's the optimal estimate you can actually derive in this setting. Okay, so now again, as I said, I'd like to keep the construction for the n. I mean, of course, you have to first construct and then do this, but let me first explain the ideas behind the control of the error term. So you see that you have, basically it's a very simple question. You have so let's forget about the two half waves again, it's just, let's consider I have only one half wave because it's the same proof. I have one half wave here, so I have this Fourier integral operator with phase u and symbol mean curvature of the u foliation, and I am trying to derive an L2 bound for this Fourier integral operator. So it's actually a very classical question. Of course, here the constraint, the difficulty is that you're on a rough space-time, so you're trying to do this in a setting of a curved manifold with a rough background. Okay, so let me before we move to the actual proof, let me do some preliminary remarks. So first of all, let me summarize a little bit some of the estimates we got this morning because we saw quite a lot of them. So I'd like to point out a few estimates which are useful to remember because that's going to serve us as a guideline. Okay, so first of all, so we have looked at the econal equation. We have extracted as much regularity as we could with respect to tx omega. We saw that it was very limited. And let me in particular, okay, so maybe let me rewrite the operator E so that you have it there. So E, this error term is given by, it's a Fourier integral operator, which is given by the integral of the two spheres, the integral from 0 to plus infinity. You have E I lambda u. So again, I'm only considering one half wave. And then I have this mean curvature, which of course also depends on tx omega. And then you have, I guess, f of lambda omega, lambda cube, d lambda d omega. Okay, so that's what you're trying to control. And here, for the explanation, of course, there are two difficulties, the fact that the phase is rough and the symbol is rough. But for what I'm going to talk, for simplicity, let me just focus on the issues having to do with the symbol, which is the mean curvature. So let's forget a little bit that the phase is rough and focus on the symbol. So let me remind you what are the estimates you can obtain for the symbol, which is this mean curvature. So for this mean curvature, the first thing we obtained was a uniform estimate. You obtain that the mean curvature is in L infinity. And then we also obtained, as far as space-time derivatives are concerned, we're able to obtain one derivative of the mean curvature in L2. I also discussed an estimate for two derivatives, but let me remind you, it was extremely weak. So it was not a functional. In other words, I couldn't estimate it as a function. So you really should think in terms of regularity that what you control is one derivative of the mean curvature in L2 along the null hypersurfaces. Okay, so you have, remind you that the way you estimate the econal equation is always by estimating it along the null hypersurfaces. So you have HU is U is equal to constant. It's the level hypersurfaces. They are null. It's the level null hypersurfaces of solution of the econal equation. And if you integrate along these null hypersurfaces, then you obtain these bounds, and then these bounds are uniform if you take the soup, both with respect to the value of u and the parameter omega. Okay? So this was it for space-time derivatives, and then we saw that when you derive with respect to, differentiate with respect to omega, surprisingly, you're also very limited, and actually it turns out you're as limited. So you also have one derivative of omega for the mean curvature is in L2, and that's it. Okay? So you're trying to control your Fourier integral operator, and the only thing you have is a uniform bound for your symbol, and then you control one derivative with respect to either omega or space-time. Okay? So now, how is this problem solved classically? So how do you derive L2 bounds for Fourier integral operators? Well, if if you look in the literature, in particular, you can open the book of Stein, which is always a good idea, and then you will see that the classical proof is something I already talked about, which is TT star. Well, actually, you always have the choice. You can do TT star or T star T, which means I'm taking my operator, so I'm taking my, so this operator is an operator acting on F. I have 4 integral operator acting on F, and I can either do TT star or T star T, which means I can either compose E with its adjoint on the left and on the right. And then what you do is you look at the kernel of that operator, and you're trying to get estimates for the kernel. Okay, you use that's how you exploit classically the oscillatory phase. You look at the kernel of TT star or T star T, that's an oscillatory integral, and start integrating by parts in this integral. Okay, and in these proofs, there is a simple criteria since you're in. Well, I mean, you could think that this acts on dimension 3T rather than a parameter. You should actually think of these operators acting in dimension 3. So you're in dimension 3, and you need a certain decay for your kernel, which in dimension 3 corresponds to, for instance, if you do TT star, that would correspond to getting 1 over x minus 1 y cubed if x and y are your variable in R3. Okay, so that means that so this clearly shows you that if you are to use this method, you should expect to have to do at least 3 integration by parts. Okay. And that's certainly something which is forbidden because we are stuck with 1 integration by part. Okay, so certainly you cannot use this classical method. So before I turn to the proof, let me just explain you why there is some hope that you can bypass this. I mean, in other words, how are we going to bypass this 3 integration by parts? So this will be a blend of decomposition from harmonic analysis, which are, I mean, fairly classical decomposition in harmonic analysis in Fourier space or in phase space. And you want to blend this with integration by parts. I mean, obviously, you expect to integrate by parts, but I want to call it geometric integration by parts in the sense that I want to make integration by parts which respect the geometry of the equanal equation. Okay, so remember, let me remind you that there are several directions, and they are absolutely not, they don't have the same, well, they are very different. Okay, so you have this L direction, which is the good one. You have E1, E2. Well, actually, no, okay, I should say L is the best one because it's in the direction of the transport for the equanal equation. Then you have E1, E2, which are good, maybe less good, but still good. And then you have L bar, which you should think of as your enemy. I mean, whenever I tell you we integrate in L bar. So in other words, what I call geometric integration by parts is that I want to be very careful when I integrate by part, and in particular, if I am allowed to integrate by part in L, I should immediately jump to that. If integrated by parts in L doesn't seem to work, I'm trying E1, E2, and if I'm really desperate, I'm trying L bar. Okay, but it's really that's the idea, I guess. And then of course you try to couple these 2 things together and see where you get. Okay, so let me try to carry out this program, but first let me show you a very simple estimate which is going to drive us through the proof, and it tells the following. So let me do a stupid estimate, which I actually already did when I derived Boolean estimates. So you, again, remember this is your Fourier integral operator, and I want to get an L2 bound, and I want to bound it by lambda f in L2 of R3. That's the correct estimate you should get. So now let's try to do a stupid estimate. So so this estimate is going to be wrong simply because I'm going to neglect the oscillations in omega. So of course, if you do this, immediately you know you lose. But it's interesting to see of how much you miss the correct estimate. So so first of all, you have the L2 norm outside, and now I'm just totally neglecting the oscillations in omega of the phase, which means that I'm taking the omega integral outside. So I'm putting the omega integral outside, and then, okay, maybe a remark. Okay, so I guess it's easier to write. So from now on, let's think of this operator as follows. Let me rewrite once and for all this operator as follows. So I want to write E. I want first to integrate in omega, in which case I have trace chi, which does not depend on lambda, so I can put it outside. And then only comes the integration in lambda, so let me write this as let me write it as this. So integral from 0 to plus infinity of ei lambda u f of lambda omega lambda cube d lambda and then d omega. Okay, I want to rewrite it like this using the fact that trace chi does actually not depend on lambda, so I can put it outside of the integral of lambda. And I want to consider these two terms like this. Okay, and this maybe let me give it a name. Let me call this f. So let me call this f of u, because once you have integrated in lambda, it only depends on, wow, okay, it also depends on omega, but it's a parameter, so let me call this f omega, f omega of u, okay? So I'm going to write E is the integral over S2, trace chi, which depends, of course, of Tx and omega, and then this f omega of u d omega. Okay, so here what I'm doing is that I'm putting the omega, the norm inside the integral, and then when I estimate the L2 norm of this guy, I'm going to estimate this guy in L infinity, this guy in L2. Okay, so this is the first line here. And now, so trace chi in L infinity, that's an estimate we derived this morning, so this one we have, so this is bounded. And now this is L2 with respect to all variables, but I'm constantly going to write L2 as follows. I think we already did this morning. I want to write L2 of M. I want to write it as L2 with respect to U, L2 with respect to HU. Right? I want to decompose I'm foliating my spacetime by a function U, so I'm decomposing as L2 in the U direction and then L2 along the null hypersurface, the level hypersurfaces of U. Okay, so in particular here, since this function only depends on U, you can forget about the L2 on HU. Don't worry about the fact that it's unbounded, that it's not really my issue here, it's more about regularity. So here, forget about this guy because this depends only on function U, so I'm left with L2 of U. And now, if I estimate this function in L2 of U, you can see that this is just an inverse Fourier, one-dimensional inverse Fourier transform. So if I take L2 of U of this guy, so if I take f omega of U, L2 of U by Plancherel, this is the L2 norm of what's inside. So this is the L2 norm of f of lambda omega lambda cube L2 lambda. Okay, and therefore, so here you have Plancherel. This is in sup norm even with respect to omega, so you can put it outside of the integral. And then inside of the integral, you're left with the L2 norm. So this is a computation we already did. You're left with the L2 norm over the integral over S2 of f of lambda omega lambda cube L2 lambda d omega. And now you do Cauchy-Schwarz in omega, and then you count the number of powers of lambda that you have. You remember that you have 2 lambda square for the volume in R3, and once you remove the lambda square for the volumes in R3, you still get an extra lambda square term. Okay, which means that when neglecting the oscillations in omega and running a quite naive estimate, you don't miss by very far. You actually miss by 1 power of lambda. Okay, and that's to be expected. This is, I mean, it's, if you think when you go from Plancherel to the stupid estimate where when you don't use the oscillations, which is you just use in L infinity, you lose square root of the frequency. So you should use square root of lambda per dimension, and since I use Plancherel in one dimension and not in the two others, I'm losing square root lambda, which gives me lambda. Okay, so it's kind of I mean this is what you should expect, to lose 1 power of the frequency per dimension if you neglect the oscillations. Okay, so now what is the idea? Suppose now I'm telling you that after all lambda is a frequency, and the frequency is like a derivative. So for some reason I can integrate by part this derivative in some, morally, and I can put it on the trace chi. If you can do this, then you obtain the following operator. Now you are left with estimating the following thing. Maybe let me. Okay, so you're left with estimating integral over S2. Now you put a derivative on trace chi, and then for your integral in lambda, I traded 1 power of lambda, so now instead of having lambda cube, I have lambda square. So this is ei lambda u lambda square f of lambda omega, d lambda, and then d omega. Okay, so you have, so here, this is a lambda square. So you have lambda, one less power of lambda, you have one derivative here, and now you run the same naive estimate. If you run the same naive estimate, so now I pick up one derivative of trace chi, and again, I have this splitting in L2, which I want to write. So here I'm estimating in the product. This one, L infinity in UL2, and the lambda integral in L2, this would be L2 of U, L infinity HU. But because it only depends on U, I can forget about the L infinity HU. We already did this computation for the Balian estimate. So this gives you the following expression. This is controlled by assumptions even uniformly in omega, so I can even remove this from the omega integral. This is under control. And then I do again the same thing. I do Plancherel. I do Cauchy-Schwarz in omega. But because now I have one less power of lambda, I end up with the correct estimate. Okay, so I think at least the heuristic here is very simple. You want to use integration by parts to trade one power of lambda against one, and pick instead one derivative of trace chi. Okay, so the question is how you can actually do this. Okay, so let me introduce the. So I told you there was some classical decomposition from harmonic analysis. So this is what we're going to use now. Harmonic analysis is about you have a big thing, you don't know how to estimate it, you cut it in little pieces, and the little pieces you know how to estimate, and if it doesn't work, you cut in smaller pieces, and at some point, hopefully that should work. So the first decomposition you do is a frequency decomposition. So it's the usual little root Paley decomposition. In other words, so we actually already did this decomposition. So you're writing your error term as a sum of pieces which are localized in a shell of lambda of size 2 to the j. Okay, so I'm having a partition of unity, right? I'm writing 1 is the sum over j of psi 2 minus j lambda, and then I guess larger than 0, and then and they are each one of them are so this is, for instance, localized in size of lambda of size between 1/2 to the 2 to the j and 2 to the j, for instance. Okay, so the point of the first decomposition is to do a second decomposition. It doesn't have a point in itself, because if you run the stupid estimate, if you think in terms of the naive estimate that we run in the previous slide, I did just trade lambda against 2 to the j. So the naive estimate loses the power of lambda. So the naive estimate for that one is going to lose 2 to the j. So you didn't gain anything by doing this. The only thing you gained is that now you can start doing a second dyadic decomposition. And now you want to do it in angle. Okay, so what I mean in angle, I started to decompose in omega. You first decompose in lambda, and then because it's not enough, then you can decompose in omega. But of course, the point of the first decomposition is that it allows you to do a second decomposition, because the second decomposition has to be related to the size of lambda, so you cannot do it first. So now I'm decomposing in angle, which means that I'm going to look at my two-sphere, because omega runs on the two-sphere, and I want to decompose it in shells. So this is my two-sphere. And I want to decompose it in dyadic shells. So so let me call this patch. So I'm going to have a patch. I'm going to decompose my sphere in patches. I'm going to have a partition of unity for these patches. The important thing is that these patches are of size 2 minus j over 2. And then in the middle, I'm going to give a name to the angle in the middle. I'm going to call it mu in S2. Okay, and I'm actually going to parameterize my partition of unity by the angle in the middle of the patch. Okay, so it's in 2 dimensions because I'm the two-sphere. So this is 2 minus j over 2. This is 2 minus j over 2. Okay. Okay, so you do this partition of unity again. You therefore, sorry, what is my notation? So eta. Okay, so my partition of unity here is called eta nu j. So j, nu is for the patch and j for the size. So it's eta nu j of omega is equal to 1 for nu in some collection. Let me call it big omega is capital omega is going to be my collection of angle on that run on the two sphere, and which essentially have distance one to the other of 2 minus Joe 2. Okay. Okay, so now you can do this second decomposition where now I'm writing this Ej nu, I'm writing it as a sum of a nu of Ej is sum of a nu of Ej nu, where nu runs of this capital omega, which is my family parameterizing my partition of unity. And I get now a new operator which is now not only localized in frequency but also in angle. Okay, and we'll see that you gain. So in particular, for instance, you can already see that you gain here, because if you remember the naive computation, at some point you take Cauchy-Schwarz in omega. So of course here, because my patch is very small, when I do Cauchy-Schwarz in omega, I'm gaining square root of the volume of the patch. And because my patch is of size 2 minus j over 2, you're gaining a power of j. It turns out to be not enough, but still you're gaining something. So already you're doing something which... Okay, so the point, of course, well, you could tell me why don't you just cut, why do you cut at this size and not another one? Well, it turns out to be the one which is the correct size for the wave equation. So you can cut, if you cut more, you're not going to succeed, and this is because of what I'm going to say now. Okay, so what do you want to do with these pieces? Of course, it's not enough to, you cannot immediately reduce to the small piece. There is still one intermediate step, which is so-called almost orthogonality. Okay, so I have written E as the sum of the EJs, but if I want to reduce to a single EJ, I first need to prove that they are, well, okay, you would like to prove that they are orthogonal, but it's not quite true. But at least you want to prove that they are almost orthogonal, in the sense that if I look at the L2 norm of the sum, it's less than the sum of the L2 norms plus something which is controlled by what you want, which is lambda f in L2. Okay, so that's what I call almost orthogonality. So that's almost orthogonality in frequency, and then of course you want to do the same in angle, because now that you are reduced to studying the L2 norm of a single piece, of a single frequency, a single parametric localized in frequency, now I want to remember that Ej is the sum of Ej nu, and I want to say that I have again almost orthogonality, so I have to prove that this is controlled by sum of the nu of E nu j square in L2. And now, of course, what I'm supposed to get is not lambda f, but it's lambda f localized in frequency, so that when I resum, this resums to the L2 norm of f, right? When I sum over j, the partition of unity is such that you will get something controllable by lambda f in L2, okay? And finally, you have reduced, if you are able to carry out these two steps, that you finally reduce yourself to the diagonal term, and then for the diagonal term, you want to actually prove the estimate. And the estimate is that, indeed, if I estimate this in L2, it's controlled by lambda f. But of course, now I need to have my cutoffs in frequency and in angle, so that when I resum in j and nu, this sums to 1, and I get the control by lambda f in L2. Okay, so this is. I mean, certainly, if you can prove this, you will prove the result. That's definite, because you'll just. This will be controlled by the sum of j, will be controlled by the sum of j and nu, which will be controlled by something which is what you want. Okay. Okay, so maybe at this stage, let me mention that again. If if you wonder why you did cut at that size, well, if you cut at larger size, you're not going to control for the diagonal term. If you cut at smaller size, you're not going to be able to prove almost orthogonality. So that turns out to be the size which is exactly right. I mean, it's a standard thing. I mean, it's certainly not. I did not come up with that size. It's a standard thing in the wave. For instance, if you consider wave packet, that's exactly the sizes that you're looking for. Okay. Okay, I guess that's it. Okay, so let me. So the way I'll proceed is I'm going to try to give you a flavor of all these steps. It turns out that the most complicated one is actually the almost orthogonality in angle. We'll see why. So let me first start with this one, which is the easiest, which is the almost orthogonality in frequency. Then I'll jump to the controlled diagonal term, and only at the end I'll come back to the second step, almost orthogonality in angle. Okay, and then we'll talk about the parametrics initial time. Okay, so let's start with the almost orthogonality in frequency. So what is it that you want to prove? Essentially, so I need to control this by lambda f in L2 localized in frequency. But of course, I need something extra to get summability, right? Because I need to, this is not a diagonal term. I'm trying to estimate the following. I mean, this, if you're used to this stuff, you know that, I mean, this is called the Klainerman lemma, I guess. Something of that sort. So you're trying to estimate sum, so what is my notation? It's sum over J and L. Sum over J, so you're trying to estimate sum over J different from L, so the non-diagonal term, in other words. You're trying to estimate this. You're trying to estimate this. Okay? So if you are to be able to resum in J and L, because you have two indices, you still need to take care, it's not a diagonal sum, so you need to get some summability. And of course, this will certainly be more than enough. It's actually, you don't need that much, but you need something which is little L1, and certainly, a negative power of J is certainly little L1. Okay, so for the Klainerman lemma, I'm looking for something which is summable here, either in J or L, so I'm looking for something which is little L1, and this does certainly the job. Okay, so let's see why you are able to get that estimate. Well, okay, so obviously this is, you expect it's a no-theta integral, so, there's only one, sorry, let me remove that. There's only one ingredient that's integration by parts. And unfortunately for us, at this stage, I cannot, you see, at this stage I did not yet decompose in angle, so I cannot really relate, I cannot really talk about tangential derivative, because what's tangential for this guy has no reason to be tangential for that one, because there is no comparison between the angles omega here. I have an angle omega in that parametrics, in that for integral operator, I have an angle omega prime here, and they are not related at all, since I am only going to compare omega and omega prime at the next step. Okay, so here, unfortunately, Indeed, I have to do the integration by parts, which I don't like, which is the L-bar integration by parts, because there is no way I can compare direction at this stage. It's not, at the next stage, once I decompose in angle, I will be able to do it, but at this stage I can't. Okay, so you'll see later what I mean with this, but here, unfortunately, there is no point in trying to distinguish the directions, and therefore, let's immediately use the worst one, which is the L-bar, which is the same as d over du. Okay, so here, remember, lambda is of size 2 to the j, lambda prime is size 2 to the L. Of course, I can always assume that, so they are different, so let's assume that j is the larger one. And therefore, because j is the larger one, you want to integrate by parts. It's more natural to integrate by part with du, because du, if you do du of E, so your phase, so remember you have Ej here, E lambda is conjugate, so the phase, one of them has, one of them has phase Ei lambda u, the other one minus Ei lambda prime u prime. And that's because there's a conjugate, so you get a minus I. And therefore, this is the phase of your oscillator integral, which you have to integrate by parts with. Okay, so in other words, my notation is that u is the function. So in other words, you have two angles, omega and omega prime, and I'm using the notation u is u of tx omega, and u prime is u of tx omega prime. Okay, because you have two omega integrals, one here and one here, so I have two angles, omega and omega prime. Okay. So I have this phase I want to integrate by parts, so I'm looking at du of this phase, and essentially du. You get, what do you get? You get du of eiu. Sorry. Oh. So let me do this computation. It's a very simple computation. You just do. Okay, so you do du of Ei lambda u minus lambda prime u prime. So this is equal to I lambda minus I lambda prime, and then I will have the dot product between the gradient of u and the gradient of u prime. Okay, so never mind this, because this is going to be of size at most 1, and this is of size 2 to the L, and this is of size 2 to the J. So if J is larger than L, this I can make, for instance, this times this, I can make it half this, and therefore this is the largest term. So this is comparable to 2 to the J times the exponential. Well, this is, of course, this is well, I mean, this is a very rough argument, but I think you can. It's still the essence of the argument, and you can still follow it. So there, never mind that it's not exactly 2 to the j. Where's my pointer? Never mind that it's not exactly 2 to the j. Essentially, what you should think is that this is the size that you get. Okay. Even, I mean, it's more messy, but this is the essence of the argument. So now I want to integrate one time with respect to u, and which is of course the u of the highest frequency here. And when you integrate by parts once, which is essentially the only thing you're able to do, because remember the symbol, the mean curvature only allows for one derivative, then unfortunately you don't get the log loss. You get the correct estimate in terms of this, but you don't get anything extra. So let me try to explain why this happens. No, actually, this one I want to keep. If we, okay. Okay, so you have j different from L. So I'm integrating by parts. So integration by parts, so I'm doing one integration by parts with respect to du. And then this gives you one, so you gain 1 over 2 to the j. And then there are two types of terms. Either the derivative falls here. Either the derivative, so it can fall on two terms. Either it falls back on this guy on the trace, so that would give you a derivative of the trace chi times, let's say, fj of u d omega, right, times el bar. That's when it falls on the highest frequency. I mean, in this business, as usual, it's always better when it falls on the lowest frequency. So the second term is going to be better in the sense that you get ej, and then you get a derivative of el. And this you should expect to be better. So this one, you should expect to be better simply because, sorry, you still have, 1 over 2 to the j is there. So what's happening is for this one, it's fine because you're going to trade, okay, so in both of them, if you want, you trade 1 power of lambda against the derivative of trace chi. So that's what you wanted to do. So this is going to yield the correct estimate because we saw that if you can make this trade, you get the correct estimate. However, in one of them, one of them is going to give you the following. You gain 1 power of lambda, and for the first one, you gain 1 power of lambda, you lose 1 power of lambda, but lambda is 2 to the j in both cases. While here, you gain 1 power of lambda, but you lose 1 power of lambda, but now the lambda is 2 to the L. Okay, so this guy is fine because you get summability, you get minus j minus L, which is what you want. This guy is not fine because that gives you 1 and you don't get summability. Okay, so in other words, after this, the only term that is left is the following one, is the one when the derivative fell on trace chi. So now, after one integration by parts, I am left with this term, 1 over 2j, so I am left with this plus OK. So now I have to reboot my integration by parts, and unfortunately I have only one derivative. I mean, this is the best estimate that I have is one derivative on trace chi. So at this stage, but however, you see, the point is that you already are at the right level. The only thing you need is summability. So in other words, at this stage I get 1 and I want summability. So this is this is not about gaining regularity. This is about gaining summability, which is very different. So summability is about putting a derivative from the highest frequency and transferring to lowest frequency. This is the only thing that remains to be done. You don't need to gain the first integration by parts. It's crucial that you gain 2 to the j. The second one, now I can just try to put a derivative from the highest to the lowest, and it's just about transferring, not gaining. Okay? So here, I do a second integration by parts, and that's where I remember, I mean, this is the point of the estimate we saw this morning where I get 2L bar of trace chi. So I'm going to decompose, so let's say that my derivative is the worst possible, it's the L bar trace chi, and I want to decompose in frequency this, so now when I say this is a physical, this is a little Pellier projector on the two surfaces, okay? So you have HU. I want to start decomposing, so I cannot really, because I'm in Lorentzian spacetime, I cannot make sense of a little Pellier projector on HU, but I can certainly make sense of a little Pellier projector on PSU, which is a two-surface which is Riemannian. Okay, so I'm defining little Pellier projections. I'm going to call P to remind that it's on PSU, on the two surfaces. And with these little loop-Pelly projections, I'm decomposing in frequency J plus L over 2, so you'll see in a moment why. And I want to look at low frequencies and high frequencies on this symbol, okay? So my symbol here, in other words, this here, I decompose. I'm starting to decompose this in frequency. Okay, so what's happening? So first of all, the easiest one to deal with is the high frequency part here, because I can actually do what I said, which is I want to transfer to the other guy. So this I can write as follows. I have, as usual, a little loop-Pelly projection. You can write it as 1 over the frequency times the derivative, essentially, right? I mean, this is exactly done for that. This is done to transfer to, you know, my little loop-Pelly projection is 1 over the frequency, which is 2 minus j plus L over 2 times the derivative of p. And now this tangential derivative, I can integrate it by parts. And because it's tangential, it doesn't see the phase u of this guy. It doesn't see this u here is transparent to the little loop-Pelly projection simply because it's defined on the level surfaces of u, so they are defined for constant u. So this guy does not see the little loop-Pelly projection. So in other words, what I achieved in this decomposition is that at least for the high frequency part, I can write this as 2, so I can put the 2 minus j. I have an extra 2 minus j minus, so j plus L over 2, sorry. And then I have this angular derivative of trace chi. And now I can integrate by part my angular derivative. And because it's transparent to the phase, because u does not see the angular derivative, it's the angular with respect to tangent to respect to u, then the derivative has to fall here after integration by parts. Okay, so that's the transfer from high frequency to low frequency. Okay, and therefore you can see that after this, immediately you will gain, because what is the difference between the other estimate? The only difference is now this guy is going to lose the power of 2 to the L. So here I'm going to lose 2 to the L, but I gain 2 minus j plus L over 2. So in the end, I still gain 2j minus L over 2. Sorry, I hope you can follow my discussion. It's getting okay, but it's just about what you gain. So here, by producing a tangential derivative, I can integrate it by part, and this is the only thing I wanted, is to transfer from high frequency to low frequency. Okay, and I still need to do it for the other one. So where's my other one? So my other part is the low frequency. Unfortunately, for the low frequency, there is nothing you can do. You have to integrate by part with the phase and not with the little loop-Pelly projector. So once you integrate, so the only thing you can do is integrate a second time by part. And if you integrate in second time by part, this time you gain, well, maybe let me not enter too much in details, but you know, this time you gain because what's happening is that you still do have so if the L bar, the worst term is when the L bar falls again on trace chi. But remember, we have an extremely weak estimate that we saw this morning. And that weak estimate still allows you to win something, because by integration by parts, you gain 2 minus j. But this little loop-Pelly projector, they are now at frequency less than j plus L over 2. So there is, you lose 2 to the j. In other words, you gain 2 to the j and you lose 2j plus L over 2. So you still gain solvability. Well, okay, there is a little caveat that you get j minus L over 4, not over 2. But let me not get into that. Okay, but again, the idea here is finding a trick to go from low to high frequency, from high to low frequency, and you see that we had to use this estimate of L bar trace chi I was talking about this morning. Okay, so now that's about almost orthogonality in frequency. So let me go back to my scheme. So here I try to convince you of this first step here, and now I'd like, again, the second one is the orthogonality in frequency in angle is the hardest part. So let me jump to the control of the diagonal term, which I think this one is quite easy to understand. Okay, so let's try to control the diagonal term. In other words, let's assume that I am able to localize both in frequency and angle, and I just want to get an L2 bound for the diagonal term, which is the following one. Okay, so it's the same L2 bound I'm trying to get from the start, except that now I'm localized both in angle and frequency. So first of all, let me do a remark that because now I'm localized in angle, there is not much difference between the trace chi at angle omega. Remember, we are in a patch. We are in the small patch of size 2 minus j over 2. So in other words, it's a very small size. and I have the angle of the middle nu. So in other words, my omega, which is in my patch, cannot be very far from this nu. Okay, it's far from almost 2 minus j over 2. Okay, so in particular, it is very tempting to say that because omega is very close to nu, I can actually put this guy outside. Okay, and then so first I put this trace chi outside, so that gives me this term evaluated at the middle of the patch, which is the nu. And then what you pick up, obviously, essentially, is the difference omega minus nu d omega trace chi, and omega minus nu, because of the size of the patch, is essentially 2 minus j over 2. Okay, so you get this new term here, and here, actually, because lambda is of size 2 to the j, essentially, let me just replace the power of lambda cube by 2 to the j, 1 power of lambda by 2 to the j. And if I remove the trace chi and I put lambda square instead of lambda cube, you recognize the original parametrics. So this is just aj nu. Okay. So here, essentially, I froze omega to be nu. I exchange lambda against 2 to the j, and you get back a relation to the original parametrics. Okay. So you'll see later on why I'm doing this, but for now, essentially, this is what you get up to this extra term. And let me first try to convince you that this term is actually already okay by itself. Okay? So why is this term already okay by itself? Well, now I can again run the naive estimate. So when you run the naive estimate, remember you lose a power of lambda. So I need to convince you that I regain my power of lambda. Okay? So first of all, 2 minus j over 2, that's square root of lambda. So I automatically regain square root of lambda. I'm only using square root of lambda. So can I regain square root of lambda? Well, you regain it because in the naive estimate, I did Cauchy-Schwarz in omega, and now when I do Cauchy-Schwarz, I'm gaining the square root of the volume of the patch. And you can see that this patch here, let me call it gamma eta j, this patch, the volume of the square root of the volume of the patch, sorry, the volume of the patch, obviously, it's essentially a square of size 2 minus j over 2 in dimension 2, so it's essentially minus 2 minus j. So when I take square root of the volume, which I gain by Cauchy-Schwarz, I gain square root of lambda. So I get square root of lambda from here. I gain square root of lambda for Cauchy-Schwarz, so I gain lambda, and I'm fine because the naive estimate only loses lambda. Okay, so this term is fine just running the naive estimate. And then it remains to use this term. So here, at this stage, unfortunately for this term, there's nothing you can do. There are no extra decomposition. However, what you want to remember now is the underlying wave equation structure. That's why I related the error term back to the parametrics. That's because, remember, derivation g of the parametrics is the error term. So if you localize in frequency and angle, it doesn't change anything in this formula. You still have derivation g of the localized parametrics is the localized error term. And now you see that the error term is related back to the parametrics. Okay, so you get a wave equation for the parametrics, which is related. So essentially, you get a wave equation with, on the right-hand side, you have trace chi inverted in the middle. You have this 2 to the j, and then you have the parametrics. But of course, because it's localized at frequency j, this is essentially a derivative of the parametrics. So you get derivation g of the parametrics is trace chi times derivative of the parametrics. And now, obviously, it seems that if you run an energy estimate, that's it. You're done. Okay. So the question is, can you indeed run an energy estimate? Okay, because here you can see the energy estimate does control one derivative of the parametrics, and on the right-hand side, this guy you know it to be L infinity, and this guy is one derivative of the parametrics. So it seems that the stupid ground wall would do the trick here. Okay, so let me still remind you that there is a caveat in the fact that the energy estimate in the quasi-linear setting has an extra term, which is a bit annoying, and I cannot use the framework I used to derive energy estimates for wave equation at this stage because I precisely need the parametrics to control the energy estimate for the wave. So here I have to control somehow the energy estimate with bare hands and hope that it works. And so let me rewrite this extra term that you have. So you had this wave equation. Now I run the energy estimate. I control first order derivative of my parametrics. I control it by the initial data, and I have to talk about this later. Then I have this term, which is just the right-hand side, and trace chi is in L infinity. But I have this extra term, which comes from the fact that in a general space-time, your unit vector field is not killing, so the deformation tensor here is not 0 in general. So you get this extra term here. And remember the deformation tensor. So you get this is the energy momentum tensor. So you get pi alpha beta, the deformation tensor contracted with d alpha s, d beta s. Okay, so that's the term that we needed to control by the parametrics for the wave equation. But now I cannot use the parametrics to control. I mean, you need to control it differently here. In other words. Okay, so here, what is the hope? Well, let me just control my time. Sorry. So the hope is that. So first of all, you see that this parametrics, essentially, it's a function of u. So basically, this should only see the gradient of u, which is L. So if you contract here, you should get an L bar here when you go down. So essentially, roughly speaking, the only thing you should say is pi contracted with L bar, and not any component of pi. And that's because, again, in my parametrics, I have this phase I lambda u, and the gradient of u is L. So when you take the derivative, you get L here, and when you contract, you get an L bar here when you go down. Okay, so it's not any component. And now if I reinject this here, you see that basically you only hope, because this guy a priori is only in L2, your only hope is to get this kind of estimate. That is, I'm going to use a trace estimate. That's the trace estimate of this morning. I first take L2 along the null geodesic, and then I take L infinity respect to the other variable. And for this one, therefore, because I took L2 in S here, unfortunately, I have to take L infinity in S because L2 in UX prime. Okay, so so let me first say that this is the correct estimate you can prove for that component. You can prove a trace estimate very similar to the trace estimates I discussed this morning. But of course, the problem is now you need to control something which is not controlled by the wave equation, right? This is stronger than the wave. I mean, if you take solution of the wave equation, in other words, this estimate is just wrong. And the only reason why we will be able to control this estimate is because it's not any wave equation. It's a solution of the wave equation which is localized in angle and frequency. And for a solution of the wave equation localized in angle and frequency, it turns out that this estimate is correct. It's just wrong in general, but it is correct if you're localized. If you have in other words, if you consider a well-localized wave packet, then you can prove this estimate. So let me just convince you that you can prove this estimate, and then I'll talk about the initial data. Okay, so so here is where we are. So you have, so you want to control this quantity again. And obviously, how can you control this quantity? This comes naturally from the transport along the direction of the null geodesics. So I want to take L nu of Sj nu, which is along the null geodesic. I want to differentiate along the null geodesic and see that I get a nice transport equation. So again, this estimate is totally wrong for a general solution of the wave equation. However, if you are localized, it turns out to be true. Simply, if you take L nu, it only falls on the phase here. Because this is the only thing depending on x. And you see that you pick an extra power of lambda from the phase, and then you pick the dot product G of L nu. L at angle omega, L at angle nu. Okay? The nu comes from here, and the omega comes from the fact that this is the gradient of u. Okay? So now the point is that here, in terms of size, so of course, there is a problem from the fact that it depends on omega, and that creates all sorts of trouble. But at least in terms of size, I want to point out that this is of size 1. Okay, simply because, well, think in terms of Minkowski. If you do this in Minkowski, you will see that you get something of size 1, simply because you have, in Minkowski, this is just, so lambda again, lambda is 2 to the j, right? And then on Minkowski, you have m of L, but L in Minkowski, remember, it's 1 omega, and the other one is 1 nu. So I think we already did this computation. When you look at Strickard's, this is 2 to the j, and then this is minus 1 plus omega dot nu. But this is simply 2 to the j. Sorry, I always get the sign wrong. I think it's minus 2 to the j omega minus nu square divided by 2. Okay? I think that's because omega and nu, they are both on the two spheres. So right? If you expand this dot product, you get exactly minus 1. Okay, so here, but of course, omega minus nu, it's like 2 minus j over 2. So this is equivalent to 2 to the j, 2 minus j over 2 square. And hallelujah, this is exactly 1, right? So, well, it's not, you have to believe in God to do this. Anyway, this computation, but it works. So, okay, so you see that this is like 1, and therefore, okay, let's just forget about the details. In some sense, you could think that this is like SG nu, okay? And then, if you look at this norm which you want to control, this is controlled by this norm by transport equation, and then because LJS nu is essentially this guy, this is controlled by L2. Okay? And then, yeah, I got lost in my, okay, yeah, sure. Okay, so the B term, you see the B term is under control because the only thing that remains to be controlled is this one. You have a trace estimate for that one. And sorry, by the way, there's a mistake. There's a square here, of course. And then, in the end, because you control this, you can essentially absorb this in the left-hand side, and you're only left with the initial data. And therefore, the only thing that remains to be done is to estimate the diagonal term at initial time. So essentially, all this was to reduce things to the initial data. Okay, so maybe it's a good time to stop. And then after the break, we'll see how to control the parametrics at initial data, and then we'll talk about the orthogonality argument in angle, and hopefully also about the parametrics at initial time. Okay, so yeah, okay, so let me remind you that, well, maybe let me come back here. So we have 3 steps to perform, which are almost orthogonality in angle, in frequency, in angle, and finally control of the diagonal term. So far, we have proved almost orthogonality in frequency. I'm going to keep the second step, almost orthogonality in angle, for the end. And then control of the diagonal term, we are almost done, except for the fact that due to an energy estimate for the wave equation, we have reduced everything to initial data. So I still need to understand the diagonal term for the parametrics at initial data. And of course, here, if you look at the diagonal term localized in frequency and angle at initial data, then suddenly there's nothing else you can do. You have to deal with that because, remember, we localized already in angle and frequency, so there's no additional localization you can do. And we went from time t to time 0. So, I mean, at some point, you have to deal with the diagonal term. So we did all the reductions we could, but now we have to deal with it. And because nothing else is left, that's where you use TT star, okay? I want to avoid TT star. I did manage to avoid TT star so far because it's rather lossy, but here there is nothing left, so you just have to hope that it's going to work. Okay, so remember, this is the diagonal term estimate at initial time. I have my parametrics localized in angle and frequency, so that's frequency, sorry, and angle, and I want to control it by lambda f in L2 together with the cutoff in frequency and angle. Okay, so that's the exact analog of the diagonal term in spacetime, and now we have reduced ourselves to this case. If you can do this, we can control the diagonal term. And anyway, at initial data, you have to do it anyway. So this is an estimate we would have to do anyway, so it's not. Okay, so what is TT star? Again, you take your operator acting on F, you multiply by its adjoint on. So you can choose the right or the left, but I'm using to multiply by I'm using TT star here, so I'm doing it on the right. And you get this kernel. So you get an operator with a kernel. And as usual in the kernel, you should always expect that you have the phase, one of the guy in the phase comes with a plus and the other one is a minus. It's because in TT star, the adjoint has a minus sign in the phase, okay? And then you have this also the integration in lambda squared in lambda the omega. So obviously my kernel in xy, I need to get some decay. And actually what I'd like to obtain is the following. Okay, you'd like to use the following usual criteria and simple criteria that you control things on L2, provided that provided you have the following. So you have your kernel depending on its y, and you want to control the sup on x in sigma naught of the integral over sigma naught of k of x, y, dy. Right? This is what you want to control. And of course, you also have to control the sup on y of the integral over x But since okay, so you have also the other one, right? You want to control this, but the other one is essentially the same. I mean, it is the same because of this. Because of the symmetry of your kernel, it doesn't quite matter. It's the same. It's exactly the same proof. So, of course, you'll just do one. Okay. So for this, we are going to start integrating by parts because there's nothing else you can do to take care of to use the oscillations. And here, first of all, notice that, of course, you can integrate by parts with respect to lambda and omega. And the good thing with respect to lambda is you're smooth with respect to lambda. So for lambda, I can, if I want to integrate by parts 10 times, I'm welcome to do it. So here, it turns out that 2 is enough. So you integrate by part twice in lambda. And what you gain, you see, if you integrate by parts in lambda, you're going to gain 2 to the j times the difference of the phases. And because I integrate by part twice, I get a square here. And if I integrate by parts in omega, so here, maybe I went fast over it this morning, but at initial data, in particular, one estimate that you get at initial data, if you push as far as you can in omega, you see that 3 derivatives of omega are in L infinity. Okay, so I am allowed. So this is, by the way, this is something which is not propagated to spacetime. It's much better at initial data. But nevertheless, I want to exploit this. So this is why it's good to reduce to initial data, is that because we made a special choice at initial data, we have actually more regulated initial data because of this mean curvature flow that we saw this morning, which is quite good because it's parabolic. So now I have this estimate. I can integrate by parts, hence 3 times in omega. And what you gain is this. You have a cube because you integrate by part 3 times. And then you can see in omega that what you gain is 2j over 2 d omega u minus d omega u at x minus d omega u at y. Okay, so here, okay, and then what are these 2j? Well, this 2j comes from, okay, so that's the estimate that you get. First of all, let me remark that I replace the angle omega by the angle in the middle of the patch. So this comes out of the integral, okay? And I replace lambda by 2 to the j. So this comes out of the integral, and you are left with the following integral. So you are left with this estimate. Of course, you have to believe me that you can put them, replace omega by nu, but let's say you can. Then you are left with the following integral. You have your estimate times the integral of S2, the integral of lambda of, what is it? Lambda square, I think it's lambda square, right? It's lambda square. So you have your cutoff in omega, your cutoff in lambda, and then you have lambda squared d lambda d omega, and this you can check easily. So first, the integral in lambda, because of your cutoff, which localizes lambda at size 2 to the j, and because of the lambda squared d lambda, you lose lambda cube, which is 2 to the j cube, and then the integral in omega, because you're localized at size 2 minus j over 2, and you're in dimension 2, you get the volume of the patch, which is 2 minus j over 2 squared because you're in dimension 2. Okay, so this gives you 2 to the 2j, and these 2 to the 2j are the 2j's that you see here, which I decided, you'll see in a minute why, to separate like this. Okay, but these are the 2 to the 2j that you get from the integral. From the volume, in other words, it's just integrating the volume of this integral and using the size of the patch in lambda and the size of the patch in omega. Okay, so here now I want to convince you that I can prove these estimates for the kernel. And here I'd like to go back to a change of variable that I already mentioned, which is this global change of variable that we have on each sigma t slice, and in particular here I have this one on the sigma 0 slice. It's the change of variable which again corresponds in the flat case to decomposing a vector in the flat case in x is x dot omega times omega plus plus d over d omega plus the component on omega orthogonal. So the d over d omega x dot omega, which is the component on omega orthogonal. Okay, so it's just this simple decomposition in omega. So this guy is along omega. This guy is along omega orthogonal. So it's this simple decomposition in R3, which you reproduced in the curve setting by producing an explicit coordinate system, global coordinate system on sigma naught. In other words, a diffeomorphism from sigma naught to R3. Okay, so I already mentioned this in connection with Strickard's estimates, but this is again useful in this setting. Okay, so here what is interesting is that here you see that you have part of your coordinate system, this part here of your coordinate system, and here you have the other part of your coordinate system. Okay, so here you should see this integral as follows. So now let me, in other words, now let me integrate it either by x, with respect to x or y, and let me use this change of variable. Okay, so I'm trying to integrate, for instance, k of x, y, dx. The other one is going to be similar. I want to integrate this on sigma naught. Okay, so that's going to be using my change of variable and my estimate. This is going to be controlled by, so you can easily see that one of them, so if I'm calling, for instance, in my change of variable, I want to call z, yeah, I don't know, maybe let me call z1 is u of x omega, and then z2 is, and z prime is du over d omega of x omega. So this one belongs to R and belongs to R2. Okay, then what I get is the integral over R. So the first estimate here it corresponds to integral over R of 2 to the j dz1 divided by 1 plus 2 to the j, what is it, z1 minus, so let me remove, so the other one by translation invariance, I can always remove this one, so let me forget about this. I mean, I just, by changing z1, actually I could have taken z1 is this minus the other one, and this is this minus the other one, and therefore I get this, 2 to the jz1 square, and the other integral is the integral over R2 of 2 to the 2j dz prime divided by 1 plus 2 to the j over 2 z, sorry, that was 2 to the j, right? 2 to the 2j over 2 z prime cube, right? Okay, so that's just by using this estimate here together with the global change of variable. Okay, so now here I want, so let me separate the integrals like this, and now let me again change variables. Let me still call it z1 and z prime for simplicity, but let me absorb the 2 to the j. So here, 2 to the j goes inside of the volume, and this is just the integral over R of dz1 over 1 plus z1 square. And the other one is simply the integral over R2 of, and again, you see that this is the correct rescaling of the volumes. Because you're in dimension 2, you're going to absorb this by your change of variable. You have 2j over 2, which is exactly the right size. And you get dz prime over 1 plus z prime cube. Okay? Okay, and therefore that's indeed finite. You see that cube, I mean, you don't quite need 3, but you certainly need more than 2. So, this, you get what you needed. Of course, here in lambda, you can get as much as you want. But certainly this, in other words, I could have done the same if I just needed d omega 2 plus delta in L infinity to conclude in some sense. Okay. Anyway, okay, so that's, so the conclusion is that indeed you get this estimate. On the other hand, this estimate is essentially the same. And because of these criteria, you know that if you get this, this corresponds to a kernel of an operator which is bounded on L2, okay? And then that concludes, and you get actually this estimate that you see here. Okay, so that's for the diagonal term at initial data. And now let me go back to the last. So again, let me remind you that in this scheme, so now in this scheme, we did number 1, almost oriented in angle, and we just did the control of the diagonal term. And now I want to prove the second point, which is alternating okay, I'm getting confused. That was alternating frequency that we did, sorry, the control of the diagonal term. And now we can move to this last part, which is the control in angle. almost alternating in angle, sorry. Okay, so almost alternating in angle, this is going to start a little bit like the almost alternating frequency. I mean, in other words, I mean, it's the same thing. You're trying to get some Kotler-Stein lemma. So you're going to estimate the non-diagonal term, that is, you're going to estimate the following integral, ej nu prime for nu different from nu prime. And remember, this is my parametrics localized in angle. So these guys are localized in angle of two patches. So here you have nu prime running in this family capital omega, which is my index over my partition of unity. Okay, maybe I should recall that. Well, let me recall you the form of my operator localized in angle, because if not, it's going to be hard to follow. So you have this ej nu. That's the integral over the two sphere of, so you have trace chi, right? And then you have your symbol trace chi, and then you have fj of u, and then you have your cutoff in omega. Okay, so this is how you should see it. And this fj of u is where you throw everything that depends on, it's the integral of lambda, so it's everything that depends on lambda. So E0, integral from 0 to infinity of ei lambda u, f of lambda omega, lambda cube, d lambda d omega. Sorry, d lambda. Right. It's the integral in lambda, okay? So you're having an integral of, oh, I forgot the cutoff, sorry. And you have the cutoff in frequency, which is psi of 2 minus j lambda. Okay, so you have the lambda, this guy contains everything about the lambda integral, and there's an index j because you're localized in frequency j. This is your cutoff in angle, which tells you that you're inside the patch of center nu, and then you have the symbol, and then you integrate over the two sphere. Okay, so this is your operator, and you're trying to prove that these two guys are orthogonal. So here, okay, so that's what I said earlier, is that now that you're, so for orthogonality decomposition in orthogonality in frequency, there is nothing, you cannot really distinguish the direction, so you have to go for L bar, which is the worst one. But now that we are distinguishing between, now that we are localized in angle, as you'll see, now you have the luxury to integrate by parts with better derivatives, which are either L or the angular derivative. Okay, so let me review. So again, as usual, you try to look to understand what integration by parts does on your phase. And remember that the phase is this ei lambda u minus ei lambda prime u prime, where u is the u of the first one, which depends on tx omega. And here, u prime is the one of the other one, which depends on tx omega prime, say. And lambda is the lambda of the first, and lambda prime the lambda of the second one, right? You have, well, each one has an integral with respect to lambda and omega, so I'm going to call lambda omega the one of here, and lambda prime omega prime the one of the second one. Okay, so you look at what, so I'm taking an angular derivative with respect to u, or L derivative with respect to u, and I want to see what you get when you apply it to the phase, because that's what you're going to gain when you integrate by parts. So you see that, first of all, this is an angular derivative with respect to u, so it does not see u, right? So this is transparent to u because this is the tangential relative to the level surfaces of u. So tangential gradient of u is 0. So the only thing you see is when it falls on u prime. So in other words, you see minus I lambda prime, angular derivative of u prime times your phase. Okay. So the question is, what is the size of this thing here? So that's easy to compute. So you have, let me go there. Let me convince you that this is the right size. But this is actually a computation. You can do the same, by the way, you can do the same computation in flat space to convince you. It's easier to see. So I need to compute, so I have this lambda prime tangential, it's a tangential derivative with respect to u of u prime. So first of all, lambda is equal to 2 to the j. And the other one is going to be, you're going to have the dot product between the gradient of u, so let's say L, and L prime, sorry, the gradient of u prime, and a tangential derivative for u. So let me say E1, EA, okay? EA is one of the tangential derivatives, okay? So its EA is either E1 or E2, but it's E1, E2 with respect to u, so it's orthogonal to L, but not L prime, right? But of course, because it's orthogonal to L, I can rewrite this as L prime minus L EA, because L is orthogonal to EA. And this is essentially d omega L, or d omega L, and this guy, d omega L, is essentially precisely this is in a tangential direction, right? So essentially, when I look at this, this is essentially sorry, no, okay, that's wrong. Of course, that's not d omega L. That's omega minus omega prime times d omega L, right? And d omega L is tangential, as we saw earlier this morning. So this is fine. This is going to be of size 1. So here, you can expect this to be of size 2 to the j omega minus omega prime, which is the same as 2 to the j nu minus nu prime. And therefore, I think I should have this thing that's written there, right? OK. So you see that you get indeed, and again, you can do the same computation in flat space to convince yourself with the phase u is t plus x dot omega, and you'll see that this is exactly what you get. OK? And then here, so that's the integration by parts with respect to angular derivatives. Now let's see what you get when you take L derivatives, which are even better. I mean, at least from the purpose of applying this to trace chi, that's the best derivative. So you have L of the phase, and now you see that you pick again, because L of u is 0, you get that you get minus I lambda prime L of u prime times the phase. And again, you can do a computation in flat space, and this I claim, so what is L of u bar? So the only thing you have to understand is what is L of u bar, L of u prime, sorry, but L of u prime is G of LL prime, and that's a computation we did already several times. If you do it in flat space, just let me do it in flat space, that's M of 1 omega prime. So as we already saw, this is minus 1 plus omega dot omega prime. I'm doing it in flat space because it's enough to understand this. So then you have minus omega. So we already did several times these computations, minus omega prime squared divided by 2. OK, so hence, you get the, if you replace it by the angle in the middle of the patch, you get this nu minus nu prime square. OK, so you can see what is the hierarchy. I mean, you can see exactly what is the trade-off. We have seen earlier that the L bar derivative gains 2 to the j. But of course, the price you have to pay is then you integrate by part with L bar, which is not so great. Here you have angular derivative. The price you pay is 2 to the j nu minus nu prime. So you gain less because you pay the difference of the angle, which is small in principle. And finally, if you integrate by part with L, which is the best derivative to integrate by part, of course, you gain still even less. So there's an interesting trade-off between what you gain according to the derivative and what you lose according to the summability. Here, you pay a nu minus nu prime square. Since nu minus nu prime you expect to be small, this is even worse. Okay, so you gain less and less in summability, but of course, what you in exchange, what you gain is that you prefer these derivatives when they fall back on trace chi. Okay, because when I integrate by part, they are going to fall back on my symbol of my Fourier integral operator, which is trace chi. So if I see L, I still prefer L because it's the best derivative. Okay, so it's a trade-off, and you have to each time to think which is the what you should do. I mean, what is the best options you have? Okay, so let me. I want to convince you that there is a log loss in this problem. If I'm trying to run the estimate a bit in the spirit I run it for the other one, for the like the volatility in frequency, I will have a problem. I will have a log loss. I won't have the same Cotlar. I won't reach a good Cotlar-Stein lemma. So let me try to convince you. So let me try to integrate first by part with an angular derivative. Okay. So if I integrate by part with respect to an angular derivative, okay. So let me. So if I do one integration by parts with respect to angular derivatives, then I'm going to gain 1 over 2 to the j nu minus nu prime. That's what's written here. And of course, then an angular derivative is going to fall on either on trace chi or trace chi bar. So let me assume that it falls either on trace chi or trace chi prime. So let me assume that it falls on trace chi. So let me assume that this is what I gain, and what I lose is the fact that it falls on trace chi. Okay, so now I get an angular derivative of trace chi. So far is essentially the problem we had. We wanted to use integration by part to gain solvability and to gain the power of lambda and put a derivative on trace chi. Of course, the only difference with the program we have in mind is the fact that you don't gain the power of lambda. You also pay an extra bit, which is nu minus nu prime, which is a bit annoying. Okay, so it's not quite what you want to do, and you'll see that you have this can be annoying anyway. Okay, now I'm going to do a second integration by parts, and here remember it's not like I have the choice, simply because I don't have any estimate for second order derivative of trace chi. So the only derivative which is good is the L derivative, because of the Ricciardo equation and the fact that I have transport in direction L, I don't have to pay. It doesn't cost me anything to take a derivative. It costs me barely anything to take a derivative in the L direction. You see that a derivative of trace chi in L direction does not cost you much because of Ricciardo, because you go back to the same regularity. Okay, so you use Ricciardo. So in other words, the only second order integration by parts you can do is L. So at least that's the good thing. You don't have other choices, so you don't have to think. So you do this. And now, so what is it that you gain? The first integration by parts gains this. So then once you do 1 plus 1 integration by parts with respect to L, then what you gain total is 2 to the j nu minus nu prime. Sorry, I'm going to get it wrong. So it's 2j over 2 nu minus nu prime cube times 2j over 2. Right? If you take this, if you take what you gain from there and there, I guess hopefully I didn't make it. Yeah, I think I made it right. So okay, so yeah, this is what you get. This is exactly what you gain, and now the following can happen. Either L. Now let me assume that so either L falls back here and I use Ricciardo and differentiate Ricciardo, or L falls on the other trace chi, I get L trace chi prime, and here I get several terms from the fact that I have to redecompose the L is on the frame with respect to u and not u prime. So I have to decompose it on the right frame. And if you decompose it on the right frame, you can easily check that the sizes that you get a size 1 for the L prime. So in other words, I'm decomposing L on the frame of L prime, and you get the following things. So you get, sorry, let me do it here. Essentially, it's the same computation over and over again. So if you do L, you get essentially something of size 1 times L prime plus something of size nu minus nu prime times angular derivatives plus nu minus nu prime square times L bar derivative prime. So all of these are prime. Okay. So the reason for that is simply that the dot. So for this one, I think it's clear that it's 1. Here, this corresponds exactly to the same computation as the one that leads to this guy, and the last one corresponds to the same computation that leads to this one. Okay, it's the same dot scalar product. Okay, so then if I apply my decomposition, I get 3 terms. The one where the component on L prime, which is 1, so I get L prime trace chi prime. I get this component here, nu minus nu prime angular derivative of trace chi prime, and then nu minus nu prime square L bar derivative of trace chi prime. So you see back this notion that there is a trade-off. That is, if I have a good derivative, I don't gain anything. If I have an angular derivative, I gain something. And if I have an L bar derivative, which is the worst one, however, I gain even more in solvability. Okay, so there is the trade-off between regularity and solvability, which you have to play with. And actually, it turns out that the worst term is the term in the middle. The both extreme terms, you can deal with them without log losses, but the term in the middle has a log loss. Okay, so let me not do the algebra. Yeah, well, I don't quite think it's. Okay, so here, what's happening here? So let me see. So you have. So first of all, so again, remember you have one. On the other hand, in this guy, I have gradient trace chi. So you have 3 terms. Either gradient trace chi times L prime trace chi prime, gradient trace chi nu minus nu prime gradient prime trace chi prime, and the last one, which is gradient trace chi nu minus nu prime square L bar prime trace chi prime. Okay? And each time, I'm trying to understand what you gain and what you lose. Okay, now maybe let me try to convince you that this is what you gain, because if not, I don't think you can really follow. So let me. Okay, so what is it? Why do I claim that you gain these things here? So first of all, this guy. So again, the only thing you gain so far is this, and now I want to. Sorry, but it's wrong. There's something wrong. It's a 3/2 here. What is it? Oh, no, it's a 3. Yeah, no, correct. Okay, that's correct. Okay, so the first one, you, in other words, okay, why do I get, there's something that I don't quite understand. Oh, yeah, no, okay, sure, okay. So you gain the following thing. You gain, so let me take care of the first one. So I have the integral over S2, and then I have gradient trace chi, and then I have fj of u times the cutoff. And then I have the second integral, so that's integral over m, and then I have the second integral where I have L of trace chi, L prime is trace chi prime, and then fj of u prime, cutoff mu prime. Okay, so this is your term, and then all of this gets multiplied by 1 over 2 j over 2, 2j over 2, mu minus nu prime cube. Okay, so what is it that you lose? So if I do I'm going to run so for this one, I'm going to say that this is from Reuschaduri. Okay, let me do this. Of course, it's not quite true, but from Reuschaduri, this behaves, it's a bit worse, but it behaves a little bit like trace chi prime. In other words, I didn't lose a derivative. So for this one, you have to believe me that you are able to prove the same estimate as for the diagonal term, that therefore this only loses, you get the right power of lambda. So you get lambda f times the cutoff. Yeah. This term doesn't lose anything. So I do Cauchy-Schwarz. In other words, I do Cauchy-Schwarz. This I treat by saying that this looks like the diagonal term because essentially by Reuschaduri this is not very different because I did not lose a derivative. And this I treat by the naive estimate because now I do the estimate where I put a derivative on trace chi and I let the integral inside the omega integral, and I know that this loses 2 to the j. This loses 2 to the j because it's the naive estimate, but because I do Cauchy-Schwarz in omega, I regain 2 minus j over 2. And then times lambda f. Okay, so now let me check that the algebra is correct. So you see that the only thing that you lose out of this is 2j over 2. So you lose 2j over 2 because you run the naive estimate, but you regain from the Cauchy-Schwarz of the patch, which is very small. You lose 2j over 2. This you don't lose because, if you believe me, that this is a little bit like trace chi, like the diagonal term. And you see that the 2j over 2 that you gain here cancels with the 2j over 2 here. And therefore, the only thing you're left with is precisely this 2j over 2 nu minus nu prime minus q. Okay, wow. I mean, there are obviously, I'm forgetting lots of details, but you know, basically this is what you should expect. And this is okay. Why is it okay? Because you're trying to get summability, and this is a correct level of summability simply because, well, you're having the same. Why is it the same level of summability? Well, I'm having to do the following thing. I have to look at, again, the same argument. I'm looking at the sum of a nu, the sup of a nu prime of my kernel. So I'm trying to look at the sum of a nu, the sup of a nu prime of my kernel, and now my kernel is 2j over 2 nu minus nu prime cube, okay? But now remember, you on the 2 sphere, you're multiplying the size of your patch by 2j over 2, so this is actually exactly equivalent to the sum over k prime in Z2. It's like you can see you're having a lattice on S2, which corresponds to lattice on Z2, and this is exactly the sum you should have in mind. Well, I guess 1 plus k minus k prime. Well, okay, it's k different from k prime. 1 over k minus k prime cube. Okay? And that is indeed summable. Okay, so then for the next term, term number 2, you're not going to be that lucky simply because, so here you get an extra bit. You get a power of nu minus nu prime. So here, you can easily see, so the difference between the previous term is that now I'm going to lose 2j over 2 for both terms, because here I'm running the naive estimate for both terms. So I'm losing 2j over 2 for both terms when I run the naive energy estimate. So now I lose 2 to the j, and I gain nu minus nu prime. So in other words, with respect to the other estimate, I have, instead of nu minus nu prime minus cube, I have nu minus nu prime minus square. And instead of 3j over 2, I have 2 to the, I have 1 less power of, I gain 1 less 2 minus j over 2. Okay, so with respect to the previous estimate, I lose 2j over 2, and I gain nu minus nu prime. So if I multiply this by the previous one, I only get minus 2 instead of minus 3. Okay, and that's the log loss, because obviously if I go back to my analogy with Z2, you can see that you have sup over nu prime, sum over nu of 1 over 2j over 2 nu minus nu prime square. That's equivalent to the sup over k prime in Z2 of sum over k different from k prime of 1 over k minus k prime square. And that's, of course, plus infinity. I mean, this is the log loss, right? This is where this sum does not converge. So this is where you have a problem. So this one, we have to think how to deal with it. But let me first convince you that the last term is also okay, that the 2 extreme terms are okay. It's only the middle term that's problematic. So for the last term, of course, so the only difference is that I'm going to run the naive energy estimate again from both of these, because I control all first-order derivatives of the mean curvature in L2 of HU. So I don't lose anything with respect to the previous estimate, except that, and I gain, furthermore, I gain a little bit more, which is nu minus nu prime square. So here, with respect to this estimate, the only difference is I can multiply this by nu minus nu prime. So I gain 2 minus j over 2, 2 minus j over 2, nu minus nu prime. Okay, so this looks like it's not better, but it is actually, for the following reason. Okay, so now, well, okay, let me remove this one. Okay, so here, this sum, actually, so again, you're having the sup in nu prime, the sum of a nu of 1 over 2j over 2, 2j over 2 nu minus nu prime. So what is this sum? This sum is equivalent to 1 over 2j over 2 sum over k of 1, so sup over k prime, sorry, somewhere, 1 over k, well, let me forget the k minus k prime, let me just write k. So you have 1 over k, and your k, but you have to remember that your k, because it comes from the, it's actually, your k is just 2j over 2 nu minus nu prime, so it's not any size, it's still less than 2j over 2. I mean, you can check that it's still, you don't run over all of Z2, you have a maximum size, which is the size when nu minus nu prime are apart from 1. If I look at 2j over 2 nu minus nu prime, when nu minus nu prime are opposite sides of the 2 sphere, this is of size 1, this is of size j over 2. So I don't get any k, I just get 2j over 2. Okay, less than 2j over 2. Okay, so here this sum is equivalent to 2j over 2, which cancels with this one. Okay, so there's no log loss for that sum. Okay, so in other words, there is only one log loss. That's the term in the middle. That's the term where when I decompose my derivative on the frame, I end up with a tangential derivative. If I end up with an L prime or an L bar prime, for different reasons, I don't have a log loss. It's for very different reasons, but nevertheless, for both extreme cases, I don't have a log loss. I only get a log loss in the middle. Okay, so here, and of course, you need to remove that log loss. I mean, you need an estimate that closes. Not if I can close at this level, if I get a log loss, of course, that destroys the whole proof. So you need to remove this log loss, and here is a way to remove it. So when you have a log loss, usually in harmonic analysis, it means you didn't decompose enough. So let's decompose another time. But because we decompose in lambda and omega, there is one last decomposition you can do. and that one is actually not standard. It's that the only thing you can decompose, because you decompose in lambda in omega, is to decompose in physical space. So I want to decompose my symbol in physical space. The symbol of my Fourier integral operator is trace chi, and now I want to relate, if you want, the size of the frequency on trace chi with the size of my other, the other sizes of lambda and omega. So I'm going to decompose with this little group Lie projection I discussed on the two surfaces quickly in the first hour this afternoon. So again, I'm taking these little loop Lie projectors on the two surfaces, and I'm decomposing trace chi with respect to this sum of projectors, okay? And now, so of course, as usual, each time you decompose, you gain and you lose, because now I need to do extra summability in this new parameter. So now I have a new parameter which corresponds to my decomposition physical space. I need also to get summability with respect to it. So I gain and I lose in some sense. Okay, so now you need to evaluate this thing. And the idea will be, as usual, to remove a log loss, I need to put more derivative on the lowest frequency. Okay, that's the main goal. So the only question here is, do you have a way of doing this, right? If I integrate by parts, there is no reason why it falls on the highest frequency. If you integrate by part, in principle, it can fall on the lowest or the highest, and you can't choose. Okay? So here, let me remind you that when we proved bilinear estimates, there was one of the bilinear estimates where precisely we faced the same problem, that we want to put more derivative on one of the terms, and for this we used the null structure of the null form to do this. So here, we need to find some analog, some reason why you can put more derivatives on the lowest frequency. Okay, so I claim that this is actually connected to the fact that, to this integration by parts in L. I want to integrate by parts in L with the L which corresponds to the highest frequency. So let's say, for instance, so I can always choose which one is highest. So let me assume that the highest frequency, that is the one with so one of them has PL trace chi, the other one PL, yeah, maybe I should, okay, sorry, maybe it's a bit, I'm starting to have too many indices, so it's a bit hard to follow. So let me just write what is the new operator we're looking for. So that's this, the following operator. So this E, so I have one index, so so AG nu L, that's the integral over the two sphere of PL trace chi. So trace chi is decomposed in frequency L, and then the rest is the same. So you have Fj of U eta j nu of omega d omega. Okay, so frequency j, angle in the patch nu, and frequency physical space, frequency L for trace chi. Decomposition of trace chi in frequency L. But this frequency here of lambda and trace chi are very different. Okay, so here I want to, in other words, so here I'm going to assume that the frequency for this L parameter here is the largest frequency between L, M and L, okay? And the goal is to put more derivatives on the lowest frequency. So for this, I integrate by part with respect to L, the L which corresponds to this guy, and not to the guy of the highest frequency. And let's see whether you can put more derivative. So what's happening? After you integrate by parts with L, either the L falls back on trace chi. So you're going to take two types of terms. You're going to get either L of PL trace chi, or you're going to get L of PM trace chi prime. That's, either it falls on one or the other. It's not like you have the choice, so it has to be one or the other. So here, okay, so now let me recall you that here I have to decompose L on the other frame. So I have to decompose L on the prime frame. So L of PM trace chi prime gives you three terms: L prime of PM trace chi prime, nu minus nu prime, angular derivative prime of PM trace chi prime, and nu minus nu prime square, L bar of PM trace chi prime, L bar prime of PM trace chi prime, which corresponds to, again, to this decomposition of L on the frame prime, on the prime frame. Okay, so now, first, let me talk about the first three terms that you get, which is L of PL trace chi, L prime of PM trace chi prime, and L bar prime of PM trace chi prime. So for these terms, I claim there is no log loss because we saw in the previous slide that we can deal with these terms without any log loss. Okay, so you'll have to believe me that you continue to do this. You still don't have a log loss. Of course, there is a caveat in the sense that I still need to regain some ability in little n and little m, so that may be annoying, and that is annoying. But certainly, at least in principle, there is a reason why you shouldn't have any log loss because they were fine from the start. In other words, the only term which is concerned with the log loss is this angular derivative prime of Pm trace chi prime. Okay, but note that in the way I did integration by parts by choosing the L, which corresponds to the largest frequency, I don't pick up any angular derivative of PL trace chi. Okay, and that's exactly what I wanted to achieve. I just achieved to have more derivative on the lowest frequency. And when I say more derivative here, I mean angular derivative because here the enemy is angular derivative. Okay, so here you design a method which allows you to put more derivative on the lowest frequency, and at least in principle, you should believe that this allows you to remove the log loss. So maybe let me try to convince you on one very simple term. There is one term which is very easy to understand. That this it's very easy to understand that you can remove this log loss looking on one term. Okay. So let me just deal. So the way you remove on this log loss. So one thing that is not written here is that, of course, you need to compare. Well, you need to compare the size of this frequency L with the J and the nu minus mu prime. So what you do is actually you compare. You want to compare 2 to the L, 2 to the M, which are the frequency associated to the decomposition of trace chi, and what comes from the angle, which is 2 to the J nu minus nu prime. So you want to compare these sizes, and you want to do different things according to the different regions. Okay? So in particular, let me show you what happens in the easiest region of them all. So again, so the easiest region. So first of all, we are assuming that 2L is larger than 2M. Okay. So let me look at region 1, which is, so you have 3 regions. You have 2 to the L larger than 2 to the M larger than 2 to the J nu minus nu prime. That's actually, so that's region number 1. So I claim that this is the easiest one. And then the other one, well, I guess the other one, they are both annoying. So you have one where you are sandwiched. One region is when this 2J nu minus nu prime is sandwiched between the 2 frequencies corresponding to trace chi. And then you have a third region where so it's the contrary. So there's a third region where 2J nu minus nu prime is larger than both frequencies. These are in principle the 3 regions that you have and that you have to deal with. So let me, at least I certainly have the time to talk a little bit about this one. So I want to show you, so this one is the easy one. So I mean, it's really, I want to show you, because here there's absolutely no integration by parts involved. So it's very easy to see what's happening. Okay, so here, let me assume that 2 to the L is larger than 2 to the M, is larger than the 2J nu minus mu prime, and let me show you that you can remove the log loss in this case, because it's really the easiest one to understand. So you have the integral of M of Ej nu L, Ej nu prime L prime, and here in this region, when you have a little Rupeli projection with a high frequency, of course, you want always to use the fact that, in this region, you want always to use the fact that PL trace chi is 2 minus L angular derivative of PL trace chi. I mean, essentially, right? And PM trace chi is equivalent to 2 minus M angular derivative of PM trace chi. In other words, if you have a little Pellet projector with a high frequency, you don't want to integrate by parts in the integral. You want to integrate by part immediately using little Pellet. So here, this gives me the following. This gives me 2 minus L minus M. And then I am reduced to the naive estimate because now I replaced essentially trace chi I'm replacing trace chi by gradient angular derivative of trace chi. Let me forget about little, well, okay, there's a PL also, sorry. PL trace chi, Fj of u eta j nu. And then same thing for the other term, where you have the angular derivative of Pm trace chi prime, Fj of u prime d omega prime. Okay, so here, what you want to do, now I can run the naive estimate because I have a derivative on trace chi. So I can run the naive estimate, and I know exactly what I lose. So I lose exactly, so it's 2 minus L, 2 minus M. And then what I lose is exactly 2 to the j. I lose 2 to the j for this, 2 to the j for this, but because of Cauchy-Schwarz, I regain 2j over 2 and 2j over 2, so I simply lose 2 to the j in the end. So I lose 2 to the j, and then I have, in particular, I have this gradient PL trace chi in L2 of HU, gradient PM trace chi, L2 in HU. Okay, and let me forget about the rest, but in terms of solvability, this is what you get, and you get these two terms here. Okay, so why don't you have a problem with that? Well, you're going to, so now, of course, you can see you have absolutely, you didn't gain anything in nu minus nu prime, so whenever you do this sum, now your sum is going to be the following. So you have 2 minus L, 2 minus M plus J, and you're going to pick up this, when you look at the summability, you're going to pick up the sum of a nu and sup of a nu prime of 1, right? So in other words, you're going to take the cardinal of the nu, so you're going to pick the cardinals of the number of angles such that 2j nu minus nu prime is smaller than 2 to the m, right? Because that's your condition. And that, because you're in dimension 2, it's very easy to compute. That gives you exactly, sorry, what did it give you exactly? So that gives you exactly 2j nu minus nu prime. That gives you 2 to the 2m, sorry. That gives you exactly 2 to the, that gives you exactly, this is exactly controlled by 2 to the 2m, 2 to the 2m minus L minus m plus j. Sorry, no, it's not 2 to the 2m, it's the nu such that this, no, it's, yeah, so it's 2 to the 2m minus, so it's 2 to the 2m minus j, sorry. It's 2 to the 2m minus j minus, what is it, minus L minus m plus j, okay? So the j cancel, and one of them cancel, and you get this extra summability 2 minus, you get 2 minus L plus m, and because L is larger than m, that's your 2 minus L minus m. So you get the summability. So once you sum in nu, you still get summability in L and m, and you can resum everything. Okay, so it's just, well, again, it's how should I say this? I mean, it's really the fact that you can a bit, yeah, okay, maybe it's not very enlightening, sorry. Maybe, now that I write it, I don't find that enlightening. It turns out to work, but I mean, you know, again, maybe I shouldn't have written this. I mean, the important point, again, is that you can put, with this strategy, you can put more derivatives on the lowest frequency, and then you can look at each of these regions. This one is the easiest one, but if you look at the other one, the region 2 and region 3, again, you can convince yourself that you remove this log loss. Okay, so so this finishes the, so again, this finishes the control of the error term, simply because now you have controlled, you have proved almost orientality in frequency in angle and controlled the diagonal term. So indeed, you get the estimate for the error term. And let me finish with a last issue, which is the construction of the parametrics. Okay, so let me remind you quickly what you want to do. The issue that you want to solve here is that here it's not only about proving estimates. Of course, there is an estimate involved, but it's also about inverting a Fourier integral operator. Okay, you have a system of Fourier integral operator, and you're trying to invert it and to say that for any right-hand side phi naught, phi 1, I can find f plus and f minus such that I can solve this equation. So it's not only about an estimate. It's inverting a Fourier integral operator and showing that the inverse of the Fourier integral operator is bounded. Okay. Anyway, okay. So here, let me simplify this, and let me just say. So you have a system at first with the two halfways. Let me just say that this reduces to proving that this scalar Fourier integral operator is invertible. Okay. So I should write QF of x. So I apply Fourier integral operator to f, and I want to prove that this is invertible. It's an invertible operator from L2 of R3, f is in L2 of R3 to L2 of sigma naught. Okay, so I'm having, this gives me something in L2 of R3, transform controlled with a change of variable. Okay, so first of all, this change of variable is the one we already saw. And the only thing I'm saying is that essentially you want to convince yourself that u of x omega, so you have a phase which is ei lambda u of x omega. I want to say that this ei lambda u omega is essentially, sorry, what is it? Yeah, okay. So I want to write u of x omega as follows. I want to write, it's just a, sorry. Yeah, this. Now I have the two of them here. Okay, so you have u of x omega. You want to say that it's u. So I want to compare it with the angle in the middle. So I want to say, first of all, I want to say that it is u of x omega times u of x nu plus du over d omega d over d omega at x nu, okay, times omega minus nu. And now I want to take so now I want to compare this with this change of variable phi nu of x, which is written on the board, and I want to compare this with phi nu of x dot omega, which would be the phase, so the phase of the inverse Fourier transform applied to phi nu is exactly phi nu of x dot omega. Okay, so I want to compare this phase with this phase, and I want to argue that they are very similar. So if I look at this phase, this dot omega, you see that I have, so my change of variable is here, so I have u of x nu times omega dot nu, nu dot omega, actually, nu dot omega, and then I have a second term, which is du over d omega of x nu times omega, right? Applied to omega. Okay, so here, first of all, you see that this, again, I'm going to use the same trick. I'm going to write this. This is nothing but, this is 1 plus O of omega minus omega prime. This is 1, sorry, yeah, actually write it as 1 minus omega minus nu square over 2 as usual. Or plus, maybe. Yeah, no, plus. And, oh, sorry, yeah, otherwise, yeah, okay. And then this here, first, because it's, because this is orthogonal to the tangent space of the spheres at nu, therefore, it's orthogonal to the, it's in the tangent space of the sphere at nu, therefore it's orthogonal to the normal, which is nu, so I can subtract a nu because this dot product with this is 0. Okay, and you see that in these phases are essentially the same up to this term. So you see that my phases are comparable. I get this is equal to this up to a term which is omega minus nu square, up to a term which is minus 2 to the j. Okay? And it turns out that essentially this is enough to conclude, and this is enough to compare. So what you are able to do is you're able to compare this operator indeed with the Fourier. So essentially what you're saying that once you're localized in angle and frequency, your Fourier operator essentially looks like an inverse Fourier transform composed with a diffeomorphism, which is this one. And now, of course, forget about this expression. If I look at this, the only thing I have to convince you is that this is equivalent. So now this is, I'm saying that this is equivalent to the norm of the Fourier transform of f localized in angle and frequency. So you have eta j nu psi j composed with this psi nu in L2 of sigma naught. But this diffeomorphism has a Jacobian close to 1. So this is essentially, because of the Jacobian, which is close to 1, this is essentially the inverse Fourier transform applied to f in L2 of R3. And then, just by Plancherel, this is essentially equal to f times the cutoff. Sorry, I forgot the cutoff. So in other words, this is going to be equivalent to the sum over j and nu of f times the cutoff, and therefore f times the cutoff, sorry, and then this is equivalent to f in L2 square. Okay, so by this observation that you can reduce everything to the inverse Fourier transform times the diffeomorphism with the Jacobian close to 1, you're actually able to show that the norm of Q in L2 square essentially behaves at the norm of L2 square up to terms that are of size epsilon. And this gives you this bound. So now this bound is correct. So this, you just prove this bound now. And because this bound is correct, you automatically get that it's 1-to-1, and that the inverse, if it exists, is bounded. The only thing that remains to do is to prove that it's on tau. And for this, you just use a continuity argument, starting from the fact that if you were in the flat case, it would be the inverse Fourier transform, which is on tau, and then you do a continuity argument, using in particular the bound that you already showed here to conclude that it's that is bijective. Sorry. Okay, so I'm going to stop here.